Welcome everyone. My name is Malte. I'm the one annoying many of you with messages on LinkedIn or private emails and stuff inviting for this event. When we talked about organizing this cross-disciplinary or interdisciplinary event, we were in doubt whether we would get 15, 20, maybe 30 participants. And last time I checked, we had actually 75 people signing up. So this is really interesting to see that so many people from different organizations, institutions, and startups are willing to be here today and spend a day with us. And it also shows that this is probably relevant to a lot of people right now to see how AI may play a role, and possibly a big role, in assessing wildlife and environmental conditions. So I think this is really, really cool. I'll not talk for long. I'll just introduce Thomas, our first speaker, Professor Thomas Moeslund, who's sitting over here. He is head of our lab, the Visual Analysis and Perception Lab at AU. He's also head of AI for People Center and head of a lot of other stuff, and I'll not mention them all because I can't remember. But he is a capacity within AI and computer vision in Denmark. So I'm really thrilled that he wanted to take his time to both make a presentation and also present today, and try to give us an introduction, a soft introduction, such that everyone is on par on what is AI, what can we use it for, what can we not use it for. So give Thomas a hand.
So yes, thank you for inviting me. Always nice to come to this building. My research field is computer vision, and been working with that since '96, mostly in academia, but also in industry. And as Malte said, I'm involved in a number of different initiatives evolving around AI. And of course, it's a thrill. Let me put it another way. So people like me were sitting basically in basements around the world, thinking about this AI thing, never really believing it going to work, but we just thought it was interesting. And then suddenly it started to work. And then we were pulled out of our basements and became rock stars and were invited for all kinds of crazy things like this today. And so, of course, that's an interesting experience. So normally when I give a presentation, I kind of decide what I'm going to talk about. That was not the case here. So Malte basically gave me some bullet points and say, you have to talk about this. So that's what I'm going to do. I am going to talk about AI, and I know for a fact that a lot of people here who know a lot about AI, so you will probably be a little bit bored. I'm sorry about that, but I kind of like Malte's idea of kind of bringing everybody up to a base, the same base level. Yes, so that's basically what I'll try to dive into today. And let me start by saying that I have been doing this a lot the past decade, going around in different communities talking about AI, from high school kids to managers. And I always had this notion of I could easily impress people, showing them things and telling stories about what we can do now and where we're going. But also had this sense that when kind of they left the room, they were kind of thinking, wow, that's impressive, but it has nothing to do. And I think all that changed when the kids started to cheat using especially chat. She just got angry, called the parents, and then the parents said, okay, what is this? And then the parents were stripped away by what this new technology is could actually do. And then they started to say, wow, perhaps AI can also transform it. And I think this is where we saw a major shift in the attitude towards AI. So now it's not just something we talk about as are we all going to die, or will we just have a fantastic world where we don't have to work? Now I think that we're talking about what does it mean for me, my life, me as a person. Technology is now not perfect, but it can now do something, I think, for all the different types of jobs that's out there. Great. So I always take the opportunity to try to say that we cannot define AI. So I've been following the different organizations, especially the EU, trying to give a good definition of what AI is. And especially EU, they actually gave up on some point. You can actually see, if you trace the definitions across time when they were doing the AI Act, you can see how the definitions changed. It's very, very interesting. And in the end, they gave up. And then they said, we're just going to do the same as OECD. So it's out of our hand. And there is, of course, a very good reason for that. And that is it cannot be defined. Of course, we have to still define it somehow. And let me give you an example. So in this room, of course, I don't know this room, but I'm guessing now a little bit. There's probably several AI systems in here. I guess there is one that pay attention to the amount of CO2 in the air. And if that becomes too high, then it would change the circulation, I'm guessing. This is an AI algorithm that basically takes some input and make a decision based on that. But there is, of course, nobody in the entire world that would call this an AI system. It's just a ventilation or whatever part of the building. But if we take this technology and go, let's say, 100 years back. So imagine you're building this room, and then you said to the engineer building it, hey, I want a room so that there should only be light in the room and there's people here. Can you please make that happen? Then the only solution they could come up with, that would be to hire a person, right, to sit and watch. So if there's other people in here, I turn on the switch, otherwise I turn it off. Because this was not possible. And if you were to describe this, you would probably say this is kind of magic or AI, if that was defined 100 years ago. So my point with this is that, and this is also the reason it's so hard to define, is that it's a fluent thing. Right now, we're talking about self-driving cars. In 10 years, we might talk about the robots terrifying Mars and stuff like that. So it will change as time evolves, and therefore it's hard to define. But it dates back to the Second World War, when we started, I was not around there, but when people started talking about, hey, what if we had a machine that could do something that we only thought humans could do? And these, what we normally refer to as rule-based systems. So if the CO2 level rises above something, then do this. So these kind of rule-based systems, they were kind of invented there, and they are all over the place still today. Then at some point, somebody said, these rules, I'm a little bit annoyed by defining them. Can we somehow learn these rules from data automatically? And that was kind of the idea that gave birth to machine learning. And then one specific algorithm within machine learning, a neural network, I'll say a little bit about that, which is now called deep learning. That was what gave the revolution we saw in 2012, to be precise, in the summer. And when you hear about AI today, normally what people mean, unless it's an advertising trick, then it has to do something around deep learning. I think it's even worse when people are quiet. I should probably just keep talking, then nobody will notice. Sorry, guys. Great. Let me give you a very, very simple but concrete example for those of you who do not work with machine learning on a day-to-day basis. So where I come from in my lab, we used to only care about doing AI for looking at other people. And one of the tasks there was to, can we make a system that take an image as input of a person and then say whether that person is this guy is called Per, or this guy Lene. So it's not that we work specifically with these two. And when we were tasked with this exercise of making such an algorithm, the first thing we would do was to look at images like this and then say, what is it that characterizes the difference between these two? And we would call that features. If we look at this, you could say, well, it seems that one of the persons here has more hair. So why don't I somehow measure the amount of hair in the image? That would be one feature that could separate these two. One is probably too little, so let me take another one. It seems that she has a more round face compared to him. So why don't I measure the circularity of the face and then let that be a second feature? And that means that an image has now been converted into two parameters. And if we map that in a two-dimensional space or a plane along these two feature axes, then this image would end up there, and the same for this. So now we have a mathematical representation of these two individuals we're looking for. Then you would say, okay, but they don't look exactly like that. Fair? Then you take a number of images. Here we have taken 10, I think, of each, and then map them out where, so this is one image, another image, and so on and so forth. So now I kind of have, and this is my training data, right? Then I basically take this data, put it into the algorithm, and then say to the algorithm, to the computer, could you please find a line that would separate these two groups of data points? And then the algorithm would say, yes, I will do that very happily for you, sir. And then it will come out with this red line. So when we talk about training an algorithm, that's basically finding this line. And when we talk about machine learning or an AI system, that is basically to say, so when then a new image I have never seen before enters the computer, then the computer would extract these two features automatically, make that into a point. This is the star you see here, and then use this rule to figure out, basically saying, is this point on this side of the line? Then it's Lene. Is it on that side? Then it's Per. That's machine learning at its core. But of course, you could have, instead of two features here, you could have 1,000,000. Then it's a little bit harder to imagine. It's the same thing. Instead of the line here, you could have something very, very complicated, but it's the same idea. So it's not complicated. You can make it complicated, but it's not. Great. So, and we have a number of algorithms that can do this for us. One of these algorithms is called an artificial neural net, and I'll not go into the details, it doesn't matter. Just think about it's a fancy way inspired by how the human brain works. It's a fancy way of finding this red line I showed you before. Not a line, but something very, very complicated. I think, of course, if you're interested in neural networks, you should learn about those. But I think the key interest to understand, if you don't know the background is this paradigm shift we saw when we went from what I call traditional machine learning to deep learning. So traditional machine learning, that was exactly what I just talked about. So imagine this was, perhaps I should have used an image of, I don't know, some fish here. Then, but you have to classify, recognize something. Then you would call an expert. That would be some of the biologists here asking, hey, what is it that separates this species from that species, and so on and so forth. And then they would call me, and I would call Stefan and Mel and say, can you please write some algorithms that can extract these features? And then you would put it into a machine learning algorithm. And so that was basically what I just said here. The new thing, is that algorithm there, machine learning, somebody said, hey, first they said, hey, let's use a neural network. Fine. Then they also said, perhaps that algorithm is better than the experts to figure out what features to use. So perhaps I should not have a human in the loop anymore. I think that's the key paradigm shift we have seen. And why is this interesting? This is interesting because it turns out that instead of giving the algorithm here features, if you give the algorithm the raw input, then the algorithm is better at figuring out which features make sense compared to what we are as humans. And that's why the algorithms sometimes are actually better at doing classification or pattern recognition, whatever we want to call it, than people are. So this is the paradigm shift I think is most important. There are others, but this, great. And then it works like a charm, and it's not perfect, don't get me wrong. And it started with images and everybody was thrilled about that. Then there was a new version of this neural network some years later, and then we could also make it work on text. And then, yeah, you know, you've probably been exposed to that also. And then in this context, so what can we use it for? And that is, of course, as Melle said, that, well, the idea here, I guess that's why you're here, is that instead of swimming out or taking a boat or however it's done, and then putting down, taking a water sample, going back to the lab and or a picture of a fish or whatever, we have the potential now to have continuous measurements. That will yield a huge amount of data, and then we need help annotating this data, right, or classifying. And this is where AI comes in. So at a meta level, what are we talking about here? We're talking about different, what we call tasks. So given an image like that, the first type of task we talk about is image classification. So you basically want to put a label on this image. What is this an image of? And then the algorithm would give you a certain percentage, and then you would just output the top one. So the algorithm would put that label on this image. Then if you zoom in a little bit, then the next level is to actually say, okay, algorithm, please give me all the objects, here it's fish, we're interested in, and what type or class they're from. So this is object recognition. So you get, and this, we call this a bounding box, this square things. So this is what comes out of the algorithm. You get bounding box around each object, and then you get a type or class. Yeah. If we zoom in even further, then you basically get for each pixel, which class do that pixel belong to? And zooming in even further, then we get the same as I just said, but now the pixels are grouped per individual. We call them individual. I don't know. So these are kind of and of course there's others. You can also do re-identification tracking or whatever have you, abnormality detection. So if the algorithm would then react to something weird it hasn't seen before and stuff like that. So this is what we call when we talk about tasks. So these are the different tasks that we can use on fish or whatever it is that we're working on. So this is the different hammers we have within AI. Okay. So I sometimes get this, this question, but isn't AI working? I've seen all the videos, I can try this and that, and where I can find the car and stuff like that. Is it working? Why are we talking about that at all? And especially those of you who work with this know it's not working perfectly. And let me give you some examples of the challenges we're faced with. So the first one, yeah, in 2012, when we had this revolution I talked about, that was a specific algorithm called AlexNet. That had roughly 60 million parameters. And I just looked up ChatGPT-4, it has 1.8 trillion. So it's not, so we have million, it's not billion, it's trillion parameters. And how do you relate to that? That's like when people say, oh, this and this amount of CO2. No, that's another thing. To give you some kind of intuition about these numbers. This is the example I showed you before. You can somehow relate these parameters to that line. Think about it like that. How many parameters do I need to represent this line? I need 2 or 3, depending on how you do it, but let's just say 2. So what I'm learning here are 2 parameters. This is the number of parameters I'm learning here. Okay. How many data points do I need to learn a line? I probably need at least 2, right? Probably more. So that means intuitively there should somehow be at least the same amount of data points as we have parameters, roughly, right? Just to give you an intuition. So if we take that intuition and go over here, it's not a 1-to-1, but just go with me here. So that means that we should have data equivalent to these numbers, not exactly the same. So can you see what I'm saying here? We need a huge amount of data points to be able to train these models, make them work, to be able to find the red line in these models. So this is one challenge. The other challenge is that it's not just about having a lot of data. Oh. I didn't know there was an audio track. That's a whale song in here. It's not just about having a lot of data. The quality of the data has to be good. Otherwise, it doesn't matter. And when it comes to subsea or subsurface quality, then there are a number of, these are the pictures we see of how it looks underwater. I have never been, well, I have actually been where it looks like this, but this is how it looks here in Limfjorden, 9 meters below the surface. This is actually, it could be much worse than this. This is from Jammerbugt. So the point here is that we have some phenomena when we go underwater that we cannot completely control and that can kind of ruin this idea of having good data points. Besides that, we also have noise from the capturing device. So the top one is from a static setup. This is where we are moving around and just getting this right, getting, a lot of stuff, just having things moving and stuff like that. So this is yet another challenge we have. And when capturing data, we also, so for instance, if we have a permanent setup, what do you do about power? How do you actually take the data from underneath the water and then to a computer somewhere? How are you doing that in practice? And we had, if you're interested in knowing more about this, talk to Malte, because he did that for a couple of years. And the only thing that saved us there was, to some degree, was that we knew some divers that were going down once a week to the spot so they could actually clean the equipment we had down there. This is something that we don't have if I put out a camera here to watch traffic or whatever. So it's a harsh environment we're talking about. This is another of the challenges. And then, of course, just finding the stuff we're looking for. I didn't see that until it was pointed out to me. Good. So it's hard to get data. Then the next challenge, that is, it has to be annotated. And by annotation, we mean that somebody has to, in the training data, to write this text that this is whatever this is, and make that bounding box or make these things. Somebody has to do that on the training data. And the more detail you want it along that axis, the more time it will take. But that's not the hard problem, because even I can probably do that. The hard part is when we're interested in details, because I can see if it's a fish and probably a shark, and that's it. But those experts here in the audience would know that, I mean, this comes as some kind of hierarchy. And if you have to put these annotated labels at this level, then there's not that many people who can do that, right? And who's going to pay for the time for doing that? Because to do this, we can hire students who are cheap, but to do this, we need experts. And we have exactly the same scenario in other domains where it's expertise that is needed. Most well known is probably the medical domain, where it's only doctors that can actually annotate some of these stuff. But there, I mean, who's paying their salary? So while you're not saving lives, you should write, yeah. So, yeah, so basically what I'm saying is we should not do AI. No, I'm not. I'm just saying that we have some huge challenges. And now something just a little bit more positive. So what can we do, if anything, about this? The first thing is that these AI models, or the general AI models, they are now rather good. And that means they can actually do a lot of the job for us, a lot of the tasks for us. And we can now build on top of those. We call it fine tuning. So think about it that you have a general model, and then we just have to change a few parameters in the model. And since it's only a few parameters, we only need a fraction of the data that we would need if we were to train the entire thing. So therefore, that actually helps us a lot. Then another thing is that perhaps it's not always that we need to know exactly which species was this fish of that passed the camera. Perhaps we're just interested in some overall statistics. So the model does not have to be 100% accurate. So perhaps it can just count roughly. When do you have activity? How many fish? What are the biomass and stuff like that? And then what we have also seen in other fields is also what we're seeing in this field now is what we call human in the loop or human on the loop. Or it's basically to say, if you have a domain where you have a lot of data, then we start by building what we call a watchdog system. And that makes sense because think about it, that 99% of the data, I'm thinking video here, contains nothing of interest. So if we can just have an algorithm that could just say, raise a flag saying, hey, there's something you should look at here. And there's something you should look at here. And the rest you can just discard. This is called a watchdog in traffic systems and stuff like that. And this is definitely something that can be used here. Also, AI might be able to, has the same knowledge as me, the general model, to say, here's a fish, there's a shark, here's an eel. I guess that's what I know. Jellyfish. And then we can use the experts only at that level. So then they only have to, is it this species of, you had jellyfish of this? Probably, yeah, I don't know. No, but this idea we see in other domains where at the course level, AI can do the job. And then for the fine-grained annotations, we can use people. Great. So summing up, AI can definitely be used to automate part of this monitoring and assessment. Perhaps not everything right now, but it's moving so quickly. So I think in 10 years, we will not be having this meeting. No, I'm guessing now. No, I'm not actually. I think then, no, stop guessing. But I think what is, at least from my point of view, is interesting here is that this is not only about, so I'm interested in the algorithms, right? But there's also this data annotation. There is whoever is going to use this for research. Here I'm thinking marine biologists. So we all become more clever. Who is going to use this for decision making? So we make the right decisions. And I think all this comes together in one big ecosystem. And this is why I think it's a fantastic thing that you have organized this today, because I think we have to collaborate together. And I think you should, again, if I were to decide, we should strive towards two things: define some joint common standards. How do we measure stuff? This is not always, that's another story. And then why don't we go for a Danish foundation model for subsea AI? There's the same talk with Danish language models. Why don't we do the same here? You can only do that, or we can only do that if we come together and help each other. Yes. So thank you for your attention.
Thank you, Thomas. We are running out of time. No, are there any questions? We have one question from the audience.
That was a little bit of a pressure.
I have one regarding the standards of this artificial modeling. I think it's very important that we try to join the forces with this, and that's also one of the things I'm gonna talk about in the panel, because it's a difficult one, but we need to have some sort of common language also, so we can differentiate between projects, and we can share the knowledge in a common data point.
Yes.
So do you have any idea of how we should get there?
If we don't do it, someone else will do it, and that will probably come from an EU level. And I'm not necessarily saying that's bad, but I'm just saying I see right now what's going on within responsible AI. And I think we have Anders here somewhere who's an expert, where Danish standard is now trying to define what we mean by responsible AI in the AI Act. And very, very few people are engaged. And therefore it ends up being random what happens. So I think if we as a community actually organize us around something, so it comes bottom up, that would definitely be my recommendation. And I don't know the industries here so well, but they have to be connected to some structures, both the private, but also the public authorities. So I think coming together and say, we want to do this. And also, I think it would give a business edge, because the moment that you have a standard that's agreed upon, then it becomes about compliance. And if you're first mover here, then your products are already compliant. So I think there's always that angle to do that together. Mm-hmm. Yes.
Thank you. Give Thomas a hand again.